Behavioral studies on vision. A typical visual behavior experiment has a visual display and an observer viewing this display. The observers are often asked to do a task, such as to report whether they see a face in the picture shown on the display screen. And the experiment observes how observers behave or react to visual inputs. For example, to observe their perception, these observers are often asked to report their perception, for example, by pressing buttons. And sometimes their gaze positions are tracked by an eye tracker, and their pupil size can also be observed by a video camera. Their brain activities can be indirectly and partially monitored, for example, by EEG or by MEG or by functional magnetic resonance imaging. And sometimes invasive observations are possible in patients during their brain surgery. And sometimes additional or alternative sensory inputs are given, for example, a sound. These are example topics in a contemporary conference on visual behavior or psychology. Don't worry if you are not familiar with some of these terms, as we have not defined them yet. They are just to give a gist of what might be. From the perspective of viewing vision as composed of these three stages, encoding, selection, and decoding, we could list some example behavioral findings according to how they may manifest these three stages. So, in this perspective, encoding is associated with sampling or image processing of visual inputs. For example, how sensitive is human vision to light? And what is the minimum difference in some of the input features that we human can still see? For example, what's the minimum difference in color, orientation, depths, spatial locations, etc., that we humans can discriminate by our visual abilities. And also many studies on visual adaptation. For example, color adaptation and the after effects such as after images. Visual selection can be linked with visual attention and segmentation. Such topics include eye movements, visual search, and visual grouping. Decoding is visual recognition, including topics such as visual illusion, face recognition, visual crowding, ambiguous perception. Of course, most visual behavior types are not confined to one processing stage, even though many of these examples can be seen as manifesting one particular stage more than the other stages. Here are some example topics that are more heavily involving more than one stage, such as active vision, visual awareness, motion processing, perception and action, and scene perception. Let's look at some examples of remarkable visual phenomena. Some of them are quite unexpected. Inattentional blindness. Can you tell the difference between these two images? We have the impression that we see all the big and small details in these images clearly. If so, you should be able to tell the difference between these two images right away. But many people cannot spot a very big difference within tens of seconds. But once I point this out to you, it's obvious. So this demonstrates that we are blind to most things in front of us. Our vision is constrained by an attentional or information processing bottleneck, such that we do not see most of visual inputs in front of us unless it's selected into our attentional bottleneck. Let's see a random dot stereogram. Here is a square array of random black and white dots. We add a smaller square array of random dots on top of it. Now you cannot see where the smaller square is because the two squares have the same randomness for their dots. We use this image as the visual input to the left eye and make a copy of it to the right eye. These are the borders of the smaller square, but without the highlight you cannot see these squares. Now if I move the small square in the left eye image a little to the right, once you fuse the two monocular images in your brain, the small square should appear in front of the big square. The brain can work out the correspondence between the two monocular images to identify this foreground square separately from the background square, even though each monocular image gives no clue of the small square. In this image, if you fixate your gaze here, you can still see the letter T to the left and to the right without shifting your gaze to them. This means that although your peripheral vision away from your gaze at this distance has a lower visual acuity, this acuity is still good enough for you to recognize the letter. However, if you add 4 surrounding letters as neighbors to this letter T to the left, keep your gaze still on the central cross. Somehow you cannot see this crowded T now, even though each neighboring letter is not overlapping with the letter T in the center of the crowd. This is visual crowding caused by something in the brain, not in the eye. If you move your gaze to it, now you can see the letter T clearly. So crowding is present in peripheral vision, but not in central vision. In this image, A is a dark square, B is a lighter square, but in fact they have the same shade for their image pixels. Perhaps more convincing to verify this way. Square B is in a shadow. The brain infers that it is lighter. In this image, you should be able to see a vivid white triangle here. But in fact, the only hints to this triangle come from these contour segments and line endings associated with the 3 black discs and this second triangle. The brain infers this white triangle so vividly that its white surface appears almost whiter than the white background. The brain also infers the 3 black discs and the second triangle from the occlusion by the inferred white triangle in front of them. A limited size of the pupil in a human eye and light diffraction mean that a point light cannot form a retinal image smaller than this area disc, and its size therefore limits the human visual acuity, and this size roughly matches the sampling spacing between neighboring photoreceptor cones at central fovea. However, if you ask a human observer to answer this question, whether the upper line in this image is displaced to the left or right of the lower line in this image, this is the vernier acuity task you are asking the observer to do, and these observers can do this task quite well even when this horizontal displacement is 10 times smaller than the normal visual acuity. And this is the visual hyperacuity, and it's most likely achieved by central brain mechanisms beyond the retina. Here you see 2 rings rotating clockwise, but in fact you can see from here that the local image pattern is simply moving back and forth and back and forth, rather than continuously moving forward. So continuously rotating clockwise is just an illusion. And this illusion is stronger in the peripheral visual field when we direct our gaze to the center of the rings so that we do not scrutinize the image patterns on the ring. Here is another illusion that's stronger in peripheral vision. You see dots flashing, but not where your gaze is staring at. These illusions likely manifest feed-forward visual algorithms in the brain. Here are many fragments, and it's unclear what they represent. Here is another version with the same fragments, but behind some occluders. we immediately recognize that behind the occluders are 5 letters B. What is in this image? It is perhaps difficult to recognize. However, after you are given a hint, now your brain can see the duck clearly without the hint. You may see a vase or you may see 2 faces. This is an example of ambiguous perception. Binocular rivalry is another example of ambiguous perception. When 2 unrelated images are shown to the 2 different eyes, the perception often alternates in time between these 2 images. If you ask an observer to look for a letter O among many letters X, it's easy and the observer's gaze will typically go directly to the target letter O. If you show most of these letters to the left eye only, but just one non-target letter X to the right eye only, the perceived image is still like the original, a superposition of the 2 monocular images shown to the 2 different eyes. This letter X, shown to the right eye only, does not appear very different from the other letters X. However, the observer's gaze is often involuntarily captured by this letter X before it moves to the target letter of this search task. There are many other examples available in textbooks and internet, etc. Understanding vision is to link the visual behavior with the underlying brain mechanisms.